Today we're going to be talking about precipitation, and the homework that you have that goes along with this assignment is due on Monday of next week, and I haven't yet loaded it onto Blackboard, but I will immediately after my classes this afternoon. Today's lecture is mainly conceptual, and then the class that we'll have on Friday is going to be a lot of problem solving and data access. I've heard that there may be a storm coming. You probably have heard the same thing, an ice storm. So we'll just have to play it by ear if the university is delayed or if things go virtual for Friday, but we'll adapt. We'll find a way forward. Stay tuned for that though. Precipitation, right? It's always in the news. People are always really interested in what the rainfall, snowfall, ice is going to be, so timely, I guess. Our class on Friday is very directly related to this topic. So precipitation begins with the movement of air, and that is because in general, where water evaporates is far removed from where it's going to precipitate. There's quite a lot of movement of moist air. And movement across the entirety of the Earth depends on several different factors. There's a lot of things that drives moisture from place to place. And you may wonder, why is there a desert in one location and a rainforest in another? And sometimes a desert will be right next to the ocean. So why is it that you could have arid dunes on the coast at one spot and in other locations just an absolutely tropical rainforest? And it's not necessarily the soil differences, it's the climatological patterns that are different. And so what we're going to do is talk about some of the factors that influence those trends. Now, of course, in one spot, you'll go through dry periods and wet periods. But what are the things that make it consistently dry in, let's say, Dubai, where they only get 4 inches of rainfall per year on average? And what is it that makes it consistently wet in West Virginia, so that we have on average about 40 inches of rainfall per year? So temperature differences as you go up through the atmosphere is one important factor, where I think everybody knows the higher you go in elevation, the colder it is. If you've ever driven up a mountain, you can sometimes notice that your ears pop, and then the other thing you maybe would notice if you get out of the car on top of the mountain is it's much cooler. So we'll learn about that trend today. There are also differences in both heat and atmospheric pressure at the boundary of air and water, where the two come together. And then even the Earth's rotation plays a role in rainfall patterns and precipitation trends across the surface of the Earth. So big picture, the first thing I want to tell you about is what's called Hadley circulation. And that is kind of a conveyor belt. You can think of it where warm air rises, cool air descends. And so think about on Earth, where is the air warm? It's at the equator. So in general, there will be rising air at the equator, and there will be descending air plunging down through the upper atmosphere to the ground at the poles, where there's less solar radiation, colder temperatures. And so now think about this as a belt. You've got this belt that's carrying, because of the rising at the poles, the rising at the equator and the falling at the poles, then it also causes a lateral movement in these mid-latitudes. And so if you're down at the ground surface, so closer to the Earth's surface, the wind is going towards the equator. And then higher in the atmosphere, the wind is going towards the pole. So hopefully that first trend makes sense because of the rising and falling. And then, now think about it, this is not stationary. This ball that's having that conveyor belt all around it is also rotating. And so that thing makes things a little bit more complicated. And so, I don't know if this animation works. Oh, maybe it will. Okay, now, what this is an animation of, what if you had a plate that spins and there's a marble on the plate? So if you're looking from above, the marble is just going from the center of the plate downward. But consider the path that the marble traces. From this side view, you get the idea of the actual path that it traced. So let this run a few more times. Although it's going straight down, from the top view, the effect of the path that's transited is this curved path. And so that kind of gives you maybe the conceptual foundation for understanding Coriolis force. All right. So Coriolis force is simply that there are these cells where both the Hadley circulation and the Earth's rotation sets up typical patterns called, you can see here, the trade winds, which are south of the majority of the United States. Like the trade winds would make it so that in Mexico and Central America, the wind typically is blowing from the east to the west, which in our mind is so foreign. Probably what you think of is whatever weather they've got in Kentucky today is the weather that we're going to have in West Virginia tomorrow. You know, just in general, the weather comes from the west towards the east, and that's because here at our latitude, we have these westerlies. And so at different latitudes on the Earth's globe, there are different patterns, different wind directions that are the combination of Hadley circulation and Coriolis forces. So that as air is moving towards the poles, it does so with a directional component, where it's going both downward towards the equator, but then also it's going sideways because of the Earth's rotation. So this is in large part why you can see at one location a desert along a coast, maybe the western coast of Africa is an example of that, where at the equator, of course, it's really tropical, but then you go north of that, and that's the Saharan desert. And it's because of the Coriolis force that we see that wide variability. So this figure just illustrates how broadly dispersed precipitation can be. And that is when it evaporates from one location, the rainfall can spread all over the place. And so this is an atmospheric model where what they did was they labeled some moisture that evaporated in South America. And they can do that by adding just a trace background of certain radiation to water and then trying to detect where it's traveled. As it evaporated, the wind blows it around, and then it finally precipitates. There's a number of ways to use tracers to study the movement of water. And so you can see that water that evaporates in the Amazon, just in a single trip, may go as far south as Patagonia, or even further south to Antarctica. And of course, in subsequent journeys, so the water in its first jump made it from here to off the coast of South America. In its second journey, it may make its way to Africa. So water is very portable because of the intensity of those trade winds. I remember seeing in the news a couple of weeks ago that they were having such incredible, the jet stream it's called. You know, like when you're on an airplane and you're traveling westward, it takes longer than the airplane journey from the west towards the east. And there was some really, really heavy jet stream effects recently where they were having record times from like Los Angeles to New York. Planes were making it faster than they ever had before simply because the wind was so high up in the upper atmosphere. And so that same wind is able to blow moisture around and really cause a lot of spatial distribution. So there are some basic forces that drive the formation of precipitation, whether it's snow or whether it's hail or just rain. There are things that in common, what they are doing is lifting air up through the atmosphere. So there's three broad categories that we'll talk about today of different things that lift moist air upward, and then that moist air precipitates downward. And this word precipitation, probably the other context that you're familiar with this word, besides the weather, what's the other place you've seen this word precipitation? In high school, you took a class where I bet you did some precipitations, right? Like chemistry lab, right. So what you'd do maybe is you'd mix two liquids together, and then precipitation would be if it was an inorganic salt, for example. A solid would form and settle to the bottom. So precipitation is like the formation of something. It is two elements being brought together that's causing a reaction. And so the same thing is similar when we think about moisture falling from the sky. It's a reaction to ingredients being put together in a certain way. So the recipe for precipitation is that air, first of all, is cooled to the dew point temperature. And that simply means that air has a certain amount of water that's dissolved in the air. You know, like if we took a cubic meter of air, it has a certain amount of moisture it can hold. And we measure how much moisture is in the air compared to how much it could hold in terms of relative humidity. And I'm sure you've heard the phrase relative humidity before. You know, if you're out in Nevada, you may feel what 10% humidity feels like. It feels very dry. You know, you'll notice your eyes get dried out. You need to drink a lot more than you do in other spots. So a really low relative humidity simply means that there's less moisture in the air than it's possible to hold. But there's an upper limit to how much moisture you can get into the air. And when you have more than that upper limit, then the water has to go somewhere else. Maybe it'll condense on the walls or condense on your windows or a glass of water. You've seen like how a glass of water sweats when there's ice water in it. Like when you've got ice in a glass of water, the reason why it's sweating is that the air that's around that cold glass is effectively losing the moisture that was in the air. It's precipitating onto the glass itself. So cooling of air is the first step of that process. And the reason why cooling is important is because when air cools, it can't hold as much moisture. Warm air holds a lot of moisture. Cool air doesn't hold very much moisture. And so by cooling, you're bringing that moisture content closer to saturation. Saturation is the limit of how much moisture can be held. There are a few different minor trends that can cause cooling, like horizontal movement of air from location to location only causes small changes in cooling. Radiation, meaning just that the air is emitting its energy, is another way to have minor cooling. But by far the most significant form of cooling that has an impact on the formation of precipitation is vertical uplift. That is, when you're raising a parcel of air, it expands because of lower pressures in the upper atmosphere, and as it expands, gases cool. And maybe you've noticed that before if you've ever recharged the AC on your car. Like they sell, if you go to AutoZone or Advance Auto, they sell these little cans of R134A. It's the refrigerant that works in your air conditioner. And so if you screw in the can to a dispenser and you plug it into your car, it's like a compressed refrigerant in the can. And as the can goes into your car, it gets icy cold. And the same thing happens like if you are spraying a lot of spray paint from a can. You'll notice that the can itself cools off. And the reason why is when a gas expands, it needs heat to do that. It consumes heat. And so when air rises, it's expanding because there's less pressure at higher elevations. As it expands, it cools. And so that vertical uplift is what's cooling off moist air and bringing it closer to saturation. Saturation is the point at which the air can no longer hold any more moisture, and then that moisture has to go somewhere. And where it has to go is onto a nuclei. So there's dust in the air, and you've probably seen it if the sun is shining in through your house at an angle. You can see all the dust particles in the air. It kind of makes you nervous to breathe if you see all the stuff floating around. But indoors and outdoors, there's all sorts of dust, whether it's sometimes in coastal areas, those small particles could be just like salt, that the ocean whipping around, little salt particles can be in the air. It can be soil from windy days. It could be fog, or the dust particles actually that's at the center of the fog could be automobile exhaust. It could be a nucleation. So this is just kind of like the small particle that the moisture begins to aggregate on as the air is cooling, and the moisture has to go out of the air because it's fully saturated. It's reached the limit to how much moisture can be dissolved in the air, so it can no longer be dissolved in the air, and it has to stick to other stuff. It sticks to these particles. And so it can stick to other water particles, like if there's a mist, which at the center is, let's say, a piece of dust, and then all around it is moisture. More moisture can go onto that droplet until the droplet is getting bigger and bigger and bigger, and suddenly the droplet is big enough that it starts to fall downward, because just like the gusts of wind can no longer suspend that droplet in the air. A very fine mist can stay suspended in the sky, and that's what you see with a cloud. I mean, that's a particle that has some moisture on it, but eventually there's so much moisture on that particle that it's heavier than the forces that are suspending it. So air cools, reaches saturation, condenses on a nuclei, the droplets grow, and then more and more water continues to get onto the outside edge of that, and eventually it falls. So here's a bit more about why air expands and cools as you go up through the atmosphere. There's something that's called the adiabatic lapse rate, and that is simply, you could draw a graph of how much cooler it is at different elevations. And you know, air is a gas, just like, and it experiences a lot of the same properties that any fluid does. Remember the hydrostatic equation in fluid mechanics when we said delta P is delta H times gamma. And when you have a tank of water, if you go down through the fluid, the pressure increases. If you go up through the fluid, the pressure decreases. Well, the same is true in the Earth's atmosphere. If here's the sun and you're going up through the atmosphere, the pressure is decreasing. Although, you know, the unit weight of air may only be around 7 newtons per meter cubed. Well, hold on a second. Well, 1 kilogram per cubic meter. Yeah, the point is it's a really small unit weight compared to over here. The unit weight of water is 9810 newtons per meter cubed. So the unit weight is so small that you have to go up a really high distance for the pressure to change much. But it is changing. So when air that's at the ground, let's say air is over a lake. The air that's right in contact with the lake is going to have a lot of evaporation from the lake go into that air. But then if it rises, that air is getting closer and closer to 100% relative humidity. Because as it's cooling off, it's reaching the saturation limit. There's an upper limit to how much moisture can be dissolved, and it's because of that packet of air expanding. There are 3 main trends that cause air to rise. Convergence is when 2 fronts come together. Like you've probably heard of warm fronts and cold fronts. So convergence is when different types of pressure systems collide. Orography has to do with the physical features of the land. So like when air runs into a mountain and is forced upward because of that. And finally, convection is when heated air rises. And we'll talk about each of these 3 in more detail. But these are the 3 things that cause moist air that's at the surface to rise. And then you'll notice here it even gives you the units for the dry adiabatic lapse rate. It says if you go up 1,000 meters in dry air, the temperature will decrease by 10 degrees Celsius. So that's how much cooler it is if you go up 1 kilometer. The Burj Khalifa is, I think, around 700 meters tall. And so if you go from the ground floor up to the observation deck on the Burj Khalifa, you can feel it. It definitely feels cooler up there. It's about 5 degrees cooler. This is the dry adiabatic lapse rate. It turns out that if the air has some humidity in it, that it's not going to change in its temperature quite so much. Instead of 10 degrees Celsius, it would maybe be around 7 degrees Celsius in moist air. But still, the basic principle is the air is cooler because of that expansion. Dry adiabatic lapse rate, 10 degrees Celsius per kilometer. Saturated, 6.5 Celsius per kilometer. Okay, so remember, lifting air is kind of the starting point of this chain reaction that causes precipitation. And so one of the things that can cause air to lift is when you have two different fronts coming together. So think about if you had a front of warm air that is over a location and cold air is intruding on the warm air. So here from A to B, this dashed line, right now we're looking from above. This is like a top view. A to B is going to be a side view that will look at a profile of this weather system here in just a minute. But the relevant things to think about here is that we have warm air that's going to be relatively higher in humidity. Because it's warm, it can hold more moisture. But the cold air is intruding over this location that has warm air. So now from the side view, here's our warm location, and the cold front is approaching. What it does is, remember, warm air rises, and so it's going to rise relatively quickly over this cold front. So when the cold front is encroaching on a region of warm air, that causes a thunderstorm. So really intense, aggressive precipitation is when you are in the location that right now is warm, but the cold air is approaching. But as the cold air approaches, it's also pushing the warm air out of the way. And so as the warm air encroaches over cool, a region of cool air that's having a warm front approaching, then that is what would cause a slower light rain. It's saying here a day-long drizzle, because it's not going to rise as quickly when the warm air is the one that's encroaching over the cool air. So it's kind of, you can predict the intensity of the rainfall based on whether a region is currently the warm region or it's currently the cool region, and what the change will be over time based on the wind patterns and the pressure at each of those locations. So this convergence, where two different pressure and temperatures of air are coming together, is sometimes also called frontal lifting, because there's the cold front that's approaching on to the warm air. There's a warm front that's approaching the cool air. So frontal lifting is one thing that can push moist air up into the atmosphere, and once it gets up into the atmosphere, remember the chain reaction is it rises, it expands, it cools, the relative humidity increases, and then once the relative humidity achieves saturation, all that extra moisture has to begin to condense on nuclei. So you really, you will have short answer questions on your exams, and I love it if students are able to explain that chain reaction events that causes precipitation. So let me run through it one more time. There's something that causes the warm, moist air to rise. As it rises, it expands. Because of it expanding, it cools. As the warm, moist air is cooling off, relative humidity is increasing until the point that you get to saturation, meaning that the air can no longer hold any more moisture. And at saturation, the excess moisture has to condense onto nucleation sites, so dust particles or salt particles that are in the atmosphere. It's condensing. Eventually, those droplets become so heavy that they fall. So that's kind of the chain reaction that causes precipitation. Another thing that's going to make this thunderstorm more intense rainfall, besides the fact that it's happening so quickly, is look at how tall the cloud is. I think this is something that we probably don't appreciate enough. We look up and we see clouds, but we can't see the thickness of the cloud cover, because all we can see is the bottom layer. So you look up, you may see clouds at 500 feet, but you can't tell, is it from 500 to 600, or is it from 500 to 2,000? So the depth of cloud cover is another factor that's going to determine the intensity of the rainfall. Any questions so far? Frontal lifting is the first. Now, this is an aerial photo of Hawaii. Has anybody here been to Hawaii before? I've only went once. And man, I hope I get to go back again because it's really a spectacular place. This is the island of Oahu. And when you're in Oahu, which is the island that Honolulu is on, they refer to the island as the windward side and the leeward side. And in case you're not a sailor, windward means it's the direction that the wind is coming from, and leeward means on the other side of the island that the wind is going towards. So if you can see, it's really green on one side of the island, and the other side of the island, I mean, you could be forgiven for thinking, was there a forest fire? Or did somebody spray defoliant? Like, why is it that it's not green on this other side of the mountain? There's a mountain range here. And it's not that anybody has removed the trees or the vegetation. It's just simply that there's way more moisture on one side of the island than the other. And this is not a very big island. And this little peninsula here is probably only 7 miles across. So there's definitely much more wet air on one side of the island than on the other. So it's because of orography. So orography is when you have a mountain barrier, and so the warm, moist air is approaching this barrier, and the wind is forcing it upward. So think about this packet of warm, moist air that is blowing along the mountain, and because it's rising, it's going through this same chain reaction that we talked about before with frontal lifting. But this time it's not because of two fronts colliding, it's just simply because of a barrier. The wind can't go through the mountain, it has to go over the mountain. So it's blowing upward. It is raising in elevation, cooling off. The relative humidity is increasing. It achieves the saturation. The excess moisture condenses onto droplets. The droplets grow until they're so heavy that they fall. So that's what's happening on the windward side. But then when that air descends, meaning goes down on the leeward side of the mountain, then it's drier than it was before because it's lost its moisture. And so there's going to be very little precipitation left once it gets on the other side, because going over this barrier kind of exhausted all of the excess moisture. And so in practical terms, you'll see that there are spots of Hawaii where on an annual basis they get 7 meters of rainfall. 7 meters of rainfall. I mean, it seems like it rains a lot here in Huntington, but we get 40 inches. That's like 1 meter. This is like 7 times as much rain. This is in the mountains. There's I don't think very many people living at this particular location, but I mean, if you contrast that to the leeward side of the island, you can see they're only getting 500 millimeters on this side. So that's a huge diversity of precipitation, and it's all because of orography. So the same thing happens if you look at our local weather forecast. They have different forecasts for Elkins versus Huntington. Like, it's always cooler there. They always get more precipitation, particularly snow. The storms are more intense in the mountain areas because the same patterns are holding there that do in Hawaii, though it's probably not as dramatic. So that was the second one, orography. And the third and final trend that causes and drives precipitation is convective lifting. My dad has this real phobia of traveling in the summer in the afternoon. He doesn't like to fly through Chicago in the afternoon because he's had so many experiences where there's some sort of an afternoon thunderstorm that delays his flight. So during the summertime, he always wants to fly in the morning because in the morning, the sun hasn't yet heated up the Earth's surface. And so it's very uncommon to have a thunderstorm in the morning during the summertime. The usual thing is that the sun will beat down on the ground for, the morning, the afternoon, and then by the late afternoon, it's warm enough that it's causing a lot of thermals that's raising, that the air is going up. You've probably seen like gliders flying around because of the thermals, just the rising air. And so if you've ever looked and seen like what almost looks like a mushroom cloud, in Kansas and Colorado, these are really common, these big clouds that form because of convection, where essentially just the sun's radiation has heated the ground, which is warm and moist, rises up, and the whole chain reaction occurs again. So convective lifting is the third and really important form of moisture that causes precipitation. So the droplets are pretty small to begin with. They could be as small as 10 to the minus third microns up to maybe 10 microns in diameter. And among the different types of precipitation, snow, hail, sleet, ice, it's rainfall that from an engineering standpoint is maybe the most important if we are trying to size drainage networks. Snow is probably the most important precipitation from a structural standpoint because, snow can accumulate on a roof and it's going to be heavy. From a transportation safety standpoint, maybe ice is the most important because it makes the surface slippery and people lose traction. But when it comes to sizing pipes, which is what we're in the business of doing as hydraulic and hydrologic engineers, is figuring out how big should the pipe or the culvert be, what width is needed for a canal or a ditch. It's the rainfall that's the most important. Initially, when there's not any moisture on these dust particles, they have a negative surface charge. And you may have learned something similar if you took environmental engineering, or is that taught this semester? How many people are taking environmental engineering this semester? Okay, some of you are in it now. Little particles of clay that are in water, that are suspended in water, repel each other because of the negative charge. And you may, if you remember back to environmental engineering, you learned about the process of coagulation and flocculation, where you're adding chemicals to try and drive down the repulsive charges so that particles can stick together. Well, initially, dust particles that are in the air, they don't stick together because they have a negative charge. But when water begins to condense and aggregate on the particles, then they're sticky in a way that they weren't when they were dry and had that negative charge. And so once they have some moisture on them, they can come together, and the impaction of two particles that have moisture, they merge together, the moisture accumulates, and that's why you can see really large hail is if there is a section of the atmosphere that water droplets, it's usually with really windy conditions, the water droplets are being blown upward, and so the water goes down through the cloud, and then the wind blows that moisture particle up through the cloud again, and it goes down, and as it's going up, it's cooling and freezing, and then it goes down through the moist air again and picks up a larger layer. So those really big hail particles are often because that accumulation of ice has gone up and down a few times due to the wind, or if it's falling through a really large layer of cloud cover that happens to have an inversion at the bottom where it's very cold. By the way, if we just go back to this, this is the adiabatic lapse rate. Usually, it's colder as you go up through the atmosphere. This is most of the time. But occasionally, there are exceptions to that where you have cold air trapped at a lower level. And so if this is the usual conditions, cooler at higher elevation. Okay, so this is elevation, and then this is like temperature. So temperature increases in this direction. So if you go up in elevation, the temperature is decreasing. There is something that's called an inversion. And inversions are more common in places where they have valleys. I used to live in Utah, and there's a lot of valleys that are surrounded on all sides by mountains. And so if you've had really, really cold weather for several weeks, and then suddenly warm air blows in, then the cold air can be trapped in the mountain valley so that it's cold down below, but if you go up through the atmosphere, it's actually warmer. And inversions cause some really interesting behavior when it comes to moisture. They trap smog and so on. But I wanted to mention it just because, usually it's getting warmer as you go up through the atmosphere, but occasionally the inversion turns things on their head. And we'll talk more about the environmental effects of inversion later on this semester. So any questions so far about any of the precipitation concepts or the growth of droplets on nucleation sites? Here's a map of our area. You can see here's Huntington, Charleston, Gallipolis. So what this is showing is different gauges where precipitation is tracked. And there's different types of precipitation gauges at certain locations. Let's say Waterloo, for example. I don't know anything specific about the gauge there, but it could be a gauge where someone is manually recording the depth of precipitation and reporting it once a day. That's probably the most widespread and the most basic precipitation tracking, is just someone who has set, like you can think of it as a graduated cylinder out in the yard, and then a ruler next to that, and just seeing how much did it rain in a 24-hour period. At the other end of the spectrum, at airports, so here at Tri-State Airport and the Charleston Airport, there are automated systems that can record how much precipitation has occurred in 15-minute increments. There are a handful of stations that record it even more often than that. I've got a little rain gauge that can give you continuous precipitation data, where anytime you have a hundredth of an inch of rainfall, it'll record that accumulation. So it's effectively ongoing. But if you download the data from NOAA, then the most resolution you can usually get is in 15-minute increments. But let's say we want to know what the precipitation is going to be in Milton. So Milton is about, from the airport, like 30 miles from Tri-State, maybe even further to Charleston Airport, where the best quality precipitation data is. So sometimes we have to extrapolate between locations where we're actually physically measuring. The other problem, besides the fact that you're in a location that doesn't have a gauge, is even if you do have a gauge, let's say here in Barbersville, looks like there's 2 gauges there, they may only have 5 or 10 years worth of precipitation data. And if you want to know how big is the 50-year storm, a gauge that's only been in place recording data for 10 years isn't going to tell you how big is the storm that only comes around once every 50 years. And so there's a lot of statistical analysis that goes into trying to solve these problems of both location and time, extrapolation, where they have a few spots where they've measured a lot of precipitation data. You know, the Charleston Airport, I think that they're going on maybe more than 80 years of precipitation data there, if I remember correctly. I could be confused because I've been looking at a lot of different airports lately, but you know, there are spots where they've got good quality precipitation data for 100 years. And so what they'll do is they'll look at, so what's the ratio of the 10-year storm to the 100-year storm? And so if they know what's the typical factor in size, then they can take that factor and extrapolate at locations, let's say in Barbersville, where if we only had a 10-year precipitation data, then we could look at what was the biggest one in that 10 years, and then use the multiplier to have a guess for what it would be on a 100-year basis. So you'll get a sense for that when we, on Friday, look at some different intensity, duration, frequency databases, and also the specific precipitation data that you can download at a given location. But the main point I wanted to make here is that a lot of the time, if you're putting in a culvert someplace, you don't have a stream gauge there, and you don't have a precipitation gauge there either. So you're having to use models to estimate what would be the flow through the stream, and also what's going to be how much rainfall that you get there. You're just relying on assumptions and educated guesses rather than actual historical data. This kind of shows you how many stations there are in the United States and how much of how long their recorded duration is. So this is a logarithmic scale, and the way to interpret it is it's saying that there's about 1,000 gauges that have, looks like, 20 years of data. But if you want to have 100 years of data, there's only, in the entire United States, only about 100 weather reporting stations that have 100 years of data or more. And when it comes to, how many places have had precipitation data recorded for more than 140 years, there's less than 10. So, I mean, probably there's one in New York, maybe one in Philadelphia, but there's not a lot of stations where they've had ongoing daily precipitation measurement for more than 140 years. So, if you're building something like a dam, you want it to survive even way more than the 100-year storm. They usually try and think about, when they're sizing how big should dams be, they think about what does the 10,000-year storm look like, not the 100-year storm. They're thinking in like epic terms. And so they really do some pretty extravagant extrapolation and look at like the maximum possible precipitation that could be in a location when they're doing things like really critical infrastructure like dams. They wouldn't rely on this kind of ordinary pedestrian rainfall data. Okay, well, I've already told you before in a previous lecture about a hyetograph. Do you remember that term from when we were talking about runoff curves? So a hyetograph is a plot of intensity on the vertical axis and time on the horizontal axis. So like, for instance, what this would show, it looks like in this case, it's every hour we have the intensity reported. So during the first hour of the storm, the intensity was a little more than 1 inch per hour, and that continued for the next 3 hours, but then in the fourth hour, first hour, second hour, third hour, the fourth hour of the storm, it seems to go up a little bit, then it goes down quite a lot. So this is the intensity on the vertical axis. If we wanted to make that a cumulative depth over time, now the vertical axis has different units. Intensity is inches per hour. This accumulated rainfall depth is, look at the January 8th storm. So at first, this is a pretty steep curve because the storm intensity is high, but then it flattens out for a little while. That means the intensity was less, but then the storm continued again. So this curve is just saying from time 0 out through 420 minutes, how much rain fell and when did it occur. So if you compare the January 8th storm, there was a lot more precipitation that day than the July 6th storm. The July 6th storm only got up to less than an inch, whereas on January 8th, it approached 5 inches of precipitation. So you need to be aware of the difference between precipitation intensity and precipitation depth, because sometimes the data that will look like will be reported in depth, and sometimes it'll be reported in intensity. And so this last slide makes that point, that if you know how many inches of rain there's been, for example, or how many millimeters of precipitation there's been, If you multiply that by the area over which it falls, then that gives you the volume of rainfall that happened. And so sometimes people will talk about, that there's going to be half an inch of ice that falls during this storm on Thursday night and Friday. That's the projection I've heard, is half an inch for Huntington. So if you wanted to melt all that ice and figure out how much runoff there's going to be from a parking lot, you'd multiply the depth by the area of the parking lot. Now, intensity is just the depth of the precipitation divided by the duration over which it fell. So drawing the distinction between precipitation depth and precipitation intensity is important. Now, recurrence interval is how I've previously described some storms in terms of how frequently they come around. So a storm that is really intense and leaves a lot of water on the ground is rare. They have a low probability. And so a storm would maybe only come around once every 50 years that has a certain precipitation depth that's really high intensity. And so instead of just talking about the precipitation intensity or the depth of water that fell, it's common for us to describe storms in terms of how infrequently they return, because we have different tolerances for risk. And we want to size certain pipes that are really important so that they can carry the 100-year storm, but then other pipes that are in areas that are less populated or where the risk of damage is lower, maybe it's okay for them to become flooded and overwhelmed more frequently. So we'd size them for a 5-year storm or a 10-year storm. Okay, so that's all for today. As a reminder, I'm going to post this next precipitation homework assignment on Blackboard. And you can, maybe I already posted it now that I think about it.
I thought you did. I think it's already posted.
It's there? Okay. Yeah, I'm always confused. So it's there already. Yeah, I remember now because I suggested you get an early start downloading that the precipitation data from online. If you can't figure that out, we're going to go over it on Friday. So I will see you then, hopefully in person, and if not, we'll just see what the weather allows.